So yesterday Manpreet might have sent a series of files, and so there is a Word file is there, and then there are couple of CSV and .text file is there. Okay. So what are we going to do? So we are going to use this Jupyter notebook slightly differently. Okay. And the only reason why we are going to use it differently, because I was two reasons. One, that I was a bit like very lazy to make a notebook like what, and second thing is like I was also a little bit busy too. So but anyways, both the things. So we will make that notebook so that, and so what we are going to learn today. So we are plot. So plotting is science as well as plotting is an art also, because what you are doing with the plotting, you are actually want to show your data in a way that the person who is seeing that should make sense out of it. Okay, it's not like you're just putting some random dots or lines together and saying like this is what it looks like. So essentially that 1,000 words. Okay, so that's what we are going to see. We are going to see, can we actually make a good picture even if we are not a Picasso or a Michelangelo, but can still be a good artist, and that is what we are going to do today. So let's start with our notebook. Okay, and then so where is it? You have these files. So there are one file called as .csv. So this one, obese sedentary. So the two obese sedentary files are there. Just drop and drag into your sidebar. Just it's in your email. The email was sent by Manpreet yesterday. So download those files onto your desktop. Okay, into one folder, and these three files. Differential gene.csv, diff underscore gene.csv, obese, those two styles which are starting with obese, those three files you drag from your folder into that zone, or you can actually upload these files from here also. Okay, you can upload, like if you do upload, and then you can actually go to the file and then you just add them and it will upload you into this one. Okay, either way you can do. So I will give you 2 minutes and to do that. Okay. So everybody got their files. It's in your Jupyter notebook now. Okay, from here we are going super fast. Okay, that's why I want that files to be there. Okay?
The other file is uploaded. The ALL file is not getting uploaded.
Which one?
This one, the ALL page.
Why?
I don't know, I'm doing this for the past sometimes.
Or you can just say, I'm sorry.
Do you want me to do extract?
Yeah, I was just, yeah. No, just I was just drop and drag there.
Yeah, I did that also. I take this one. This one going.
Re
Close and
yeah, maybe download it and then, yeah. Okay. Okay, you guys have, everybody has the files in their Jupyter notebook? Okay, extra 30 seconds. This is what Francis gave you. And those who already added your file, please open that Word file which says basic R plotting. Okay. Anybody need help? Okay.
Extract those files first.
It's a zip file, format.
Oh, okay.
No, you don't need the document.
Which
You only need the
document
three
we need
files.
to open?
No, you don't have to open any. There's a Word file called as, not in the Jupyter notebook, outside Jupyter notebook. Open that file called as basic R plotting. Eh? Okay. Everybody is fine. Okay. So
Hold on. You need to upload three files. The one that is copy, the ones that are not documents.
yeah, there are three files only there which are not docx files. These are not Word files. You just load those three things in your Jupyter notebook. Okay.
One extra minute.
Yeah, that's fine.
All of them are that CSV file.
Yeah, yeah. You just, I think two files are CSV, one is .text file, I believe. Is that right? All three are CSV? Okay. Okay. Okay, let's actually start. What I'm going to do, I will be actually going backward and forward from the Word file to Jupyter notebook and Jupyter back to this. So R, unlike many other uh, programming language, where you can actually, when you want to access a file, what you do, you actually give a path of that file, and you can any program can directly access that through the path. So that means you, like a Linux, if you are running a fastq, what you are doing, you are actually say fastqc, and then you tell your file name. If you are not in that particular working directory or folder, then you will say give the whole path, and it will take the data from there and execute your. But in case of R, that is now how it works. Okay. So, but before that, see, I am not here to teach you R. Okay. I am actually going to teach you how to use R for your application. So, I am not going to give you any theoretical aspect of R programming. So, that is why I am going to give you a little more practical way how you can approach it. So, first thing what you need to do, R has a workspace. So, if you use R Studio or you are using R Terminal, or in Jupyter Notebook, you are actually using the R workspace for the executing your. So, every data that actually you want to analyze, plot, and anything, you need to call that into the workspace and store that as an object first. So, the first thing what you need to do, even if you have all the files, everything, the first thing what you need to do is to store that as into our workspace as an object. That is what the word actually is, object. Okay. So, you store them as an object. Now, there are various ways to store your data as an object. I am not going to too detail into that. And there are commands like the usual command that is used for storing a R data into R space into the R workspace is called as a read commands. So, you can use read.csv for CSV file. You can use read.delim for tab delimited files, and there are other options for reads are also available, and you can modify some of this for when you go for a higher thing. But for time being, you can use read.csv for your reading your file into R workspace and storing that as an object. Now, Francis was yesterday using that sign like dash and greater than sign. He's always doing programming, so it comes easily for him to type like that. I actually does very rarely. That means, so that is why I type always I do equal sign, and so both the equal sign and that sign both are. If you can actually do fast and you can do like with the what that called? Yeah, it's actually yeah. So you can do that, but you can still use equal to also. Okay, so let's actually first start with copying this, and I will explain you what this means, and then we will go for the next. So just this line of code you copy and paste this into your code, and Just leave it, don't do anything at this point. Okay. Now, what are we actually trying to do here? We are actually trying to create an object called as DE. So, because this is a differential gene expression table, so I actually gave it name. So, always be explicit with your with your object name, because you might be creating multiple objects during your programming, and at some point you will lose track of it, that which is what. Okay. So, you do this DE and equal to, that means whatever I am going to read into will be stored as an object as DE. Okay. Now, I know that my file format is CSV. So, that means I am actually going to use a command called as read.csv in this case, and I am actually use read.csv, and I open the parenthesis and within quotes. So, when you have a file name, it is always within quotes, and if it is an object, it should not have quotes. So, when I am going to read DE, I should not use quotes, but when I am reading a file, I need to use quotes. So, since I am reading a file, and my file which I am interested to read is sig_gene. So, basically I am just looking for significant genes which is in CSV format. So, read.csv, and this is the simplest way of, you can actually have more complex construct of this line of code, like you can skip certain lines, you can change header, so many different things you can do with this command, but for time being we just want to read this file and save that as an object called as DE. Okay. So, now let us run this. Okay. So, now it seems what computer is telling me that it saved this file as DE, but then how we know that we saved this file? Either I have to believe Francis, because he is the one who uses Jupyter Notebook all the time, or we have to find some ways to test it. Okay. So, that what it means, like if we run this code and code is successful, that means our workspace has an object called as DE. So, there are one way of doing it is to, you remember yesterday Francis used a command called as ls. So, use ls and then parenthesis open and close like this, and then if you run this line of code, it will show me that there is an object called as DE there. Okay. But still we do not know what is there in that DE. So, again Francis showed me yesterday another command which was head. So, if we actually use head and we say DE and if we run it, it will show you the top 10 lines of that file, and you know how your file looks like. So, you can actually see that what is there, the content of the file. Okay. Now, these files are usually like big files, 20,000 lines, 30,000 lines. You also need to know that whether whole file was captured or not. Okay. So, for that you will use something called as dim or dimension of the file. Okay. So, if you use dim command, then it will give you that this file has 523 rows and 13 columns. So, I always love to joke that R is a Roman Catholic, because R everything actually the first is row and second is column. So, it is RC. Okay. So, what are the things we looked at? We checked whether we have an object in our workspace. We looked at what is the dimension of that object. We also checked what it looks like. Okay. And we can also ask like what is the columns, what are the different columns in this, call names actually, and then we say DE. I think it is. Okay, let me check what it is, but no, it is. So, you can use other command called as str. If you are using this command called as str, it will give you what are the different columns are there, what are their characters, and it will show you some values which means nothing. Okay. Before str we are actually using head, and str should be fine, dim. So as I mentioned, as soon as
Say something. Remember white spaces? What I said yesterday. Never use them. They're redundant pretty much.
yeah,
So, and command, between a command and the parentheses, never white spaces. When you write the string, you never use white
Yeah.
spaces normally, right?
always if you have two words, you always connect that with an underscore. That is the best convention. Okay, you want to name it like two. Yeah, no, so basically we have 4 commands which we think about: head, ls, dim, and str. So basically what we are doing here, you got a data, doesn't mean that you should just, as soon as you get the data, I'm going to start plotting it. You need to, so what do you do when you go to a grocery store? What do you do? Grocery store means to buy, okay, you go to buy a vegetable, what do you do? Eh? No, but before that something else you do. Yeah, you look at vegetable, you smell them, you see like they are, smushy or something. Eh? So basically you need to know that if vegetables are good, they are not dried or something. So any data that you get, you should first know that what I was expecting to be loading into the space is there. So you are looking at how many rows are there. So you are using dim command for that. You are looking for dimensions. So it will give you how many rows and how many columns are there. Did you run that dim command, all of you? And then you are using str. Basically you are using structure of your, so it will give you all this different columns and its name and all those kind of things. Eh? And then you are looking at head, and you can also use another command called as tail, tail, tail. You can type that and see what you find in tail, tail, just tail parenthesis de, then parenthesis close. Eh? Yeah, the last of the file. So you also want to know that if all the files were copied or not, because some truncation happened. So basically the moment you get a file, you should not start doing everything with it. Just check, yeah, this is what you are expecting from your file, and is it everything there? Okay, so everybody is with me at this point?
What is D here? Name of the file?
Yeah, it's an object that we stored. So the file, we actually use read.csv, and we stored the content of that file into an object called as de.
D is the name given by
You gave the name.
All right.
Yeah, you give any name, you can give my name also, I'm fine. Okay, okay. So now then we use ls, and we saw that our file is there, our object is there, not file. Okay, our object is there. So now go to the second line of command. Eh? And don't run it. I will just okay, just copy the second line and then put it here, and then we'll discuss what this code is about. Okay. No, this is only one line. Did you? There's not 2 line. Okay. Okay. Let's think little bit more about this command, what we are doing here. Okay. So my aim is to plot something. Eh? I want to plot something. Okay. Just forget about what I'm plotting. So no, I'm defining. So that is where I'm coming to. I'm actually interested to plot whatever I'm actually interested to plot a scatter plot. It's a 2-dimensional data. That means we need an x and y, and the x in my x-axis I want to use the column which is obese sedentary dot filter dot count dot mean. This is the column name. So you see this str showing you this all the column names. So there is one of the column which it says the column name is obese dot sedentary dot filter dot count dot mean. That is a column name. Okay, and the second column that I want to actually plot on y-axis is base mean. There is a column name called as base mean. If you actually open your Excel file also, you can see those 2 columns are there in your you can just check with the Excel file that if those columns are there. Okay, So now how you define a column? So we have an object, its name is DE. So if you use a dollar sign and then in front of after dollar sign you write the column name, and that is the how you define a column. So now with the DE dollar sign the column name, then comma the second DE column, and so this is what we are, and then what we are doing, we are just saying plot. So plot parenthesis, define the first column, then define second column, parenthesis closed, and run it.
How is it making sure that whatever we are putting in the first will be the x-axis, will be on the x-axis?
Yeah, because the first is always x axis and the yeah, that is default. So x and y, that is how I actually define. Okay.
Plot, what does plot mean here? I haven't given the command to the scatter plot banana.
No, the plot when you do it is a scatter plot.
Always.
Yeah, we'll see how other plots are made in this. Okay. So plot, when the moment you give the plot, it is expecting you to have two columns because it's a two-dimensional scatter plot that we are looking at, and then we defined both the columns using the dollar sign. So object DE which we created, dollar sign, the column name, comma, again the second column that defined by DE dollar. So what is the problem with this plot? Do you like to report this plot? You want to show this to your supervisor? Okay, so it's a very bad plot. Okay, but before we really do that, why don't you choose any two columns with a numerical value and plot them in x and y, 2 or 3 times different from the same object. You know, this time I choose these two. You choose any two columns and just plot. Make sure like you can run them. What is this? Oh yeah, like that. So just try two, three different columns. So I just want you to learn how to select a column and then just plot it. नहीं एक्सेल शीट में नहीं, हाँ नहीं एक्सेल शीट वाला ये वही है. Yeah, you can figure out the names from there if you want, but otherwise you have those names in. If you use str command, you will get that. What is the column names command, Francis? You remember call? It's just call, no? It did not work actually. Call names for some reason. Call names. Oh, okay. So here is a command. Okay, if you use this command, call names, COLNAMES, and then you within the parentheses you give your object name. It will show you all the columns there. Okay, and then pick the one which has a numerical value and just plot. Just two random columns you pick and make a plot. Okay, you have 2 minutes to do so. No, just use this call name. So you have done already. So basically you can use call names to find which are the columns, and then yeah, fine. So make couple of them. So you learn how to actually pick a column and then use plotting. Okay, everybody is fine, everybody is comfortable. Okay, so now we made a very shitty plot which we can't even show to ourselves. Okay, that's such a bad plot we made. So what is the problem with this plot? You have any idea why? Yeah, because actually the biggest problem with this plot is that there is one outlier here. You see that one? This outlier. Because of this outlier, all the other data is actually squeezed. So one way of doing it, if we create a threshold for our y-axis and x-axis, and then that means what happened, that one outlier will be threshold to a lower value, and that will increase the spread of the data. But looking at it, we don't know what might be the values. Okay, so we can actually guess something like 10,000 or something will be the value here. So what I will do, where is it? So if you go to the third line of command, copy that and just wait for me to. Okay, so just copy this line of command. Okay, did everybody copied this command? So see, the first part of this is same what you already did. You are plot, then you choose those two columns, and then you have now you have a new set of command which is called as xlim and ylim. So what you are saying that what is the threshold for x and y. So here I am defining the x limit as 0 to 10,000. So I want my x axis up to 10,000 and y axis up to 10,000. Okay, and let's actually run this. So this is how now it looks like. Okay, so which means that it's not that bad, but I want little more spread. Data needs to be little more spread on my scatter plot. So what I can do, I can actually change my x and x limit and y limit value. So I will actually go and change maybe 5,000 and 5,000. So one thing you should remember here, you don't have to match values. So if it is x like 0 to 4,000, then y can be 0 to 10,000 also. So you don't have to be, those values need not be equal. So you can change those values, and then so it is giving you something like that. So what finally we could do, okay, let's actually try with 5,000. Okay, so what I want now you to do, you create different plots with changing x and y axis values and see like how those plots looks like. Okay, so everything done. Okay, next thing, I personally don't like black dots, and then I want it to be a little more colorful. So I like to define a color, and the one way of doing it using an extra command called as call, which is basically, if you actually copy and paste this. So I have this one. So see, all this is same. You have DE, you actually did the plot, and from the plot you have the columns, and after the columns you have xlim and ylim values. And now we added a extra command called as col. And since we are actually giving a text, so that is why it is within the code. So if you are, so you can write blue, you can write green, you can write purple, and it will give you those colors. So you can actually try a couple of colors, run them, and try a couple of colors. So now my plots are red in color. So from the black, now I am at red. Okay, so everybody is fine till now. You can change colors. What about you? Okay, now I did this, but the problem is that I don't like those open circles. They look pretty ugly to me. Okay, so there is a command called as PCH. Okay, and using PCH you can assign any shape to your plot. So in the Word file, you can see I have given values for PCH. So if you are using PCH is equal to 0, that means your dots will now open circle will become square. If you are actually using 1, then it will become circle, like that. So if you are looking 18, then it will become a diamond. Prod will become diamond shape. So let's try few of the pitch. So I'm going to use pitch 9, this value PCH 9, which corresponds to diamond plus. Okay, so as you see, what I did, I actually just added PCH is equal to 9, and then okay. So one thing, so are you able to appreciate one thing, that what I am doing here, I am actually adding more and more commands within the parenthesis. I am not going outside the parenthesis, and I am separating each of these syntaxes with a comma. Okay, so I actually added a new syntax called as PCH is equal to, and my choice is for diamond plus. You can choose anything you want. The numbers are given, and if you run them, now my graph will see, it looks like a diamond plus there. So you can change this to any shape. Would you like to try a couple of shapes? Okay, great job. So I have done that. Now, sometime I like to add a vertical line saying like this is my limit and anything beyond this and above this. So that's called as ab line or absolute line, AB lines, okay? And you can use a command called as ab line. So just copy this, and this is actually done slightly differently, so I would like to actually talk about this. So in case of okay, in case of absolute line, the ab line command actually comes outside the parenthesis. So all this time we were actually adding more and more commands inside the parenthesis. Here the first time we actually closed our parenthesis and started a new line, and we defined what is the absolute line. So AB is equal to V is equal to 2. V means we are talking about vertical line. So if you are plotting a vertical line, then the command is V, and then we are telling where the vertical line should be, and it is at the position number 2. So if you actually say 2000, it will make a line. So let's run this and see what happens. So see, now it is at 2. If I actually change this to 2000, my line position changed. So I can actually so basically you finish so whatever last time commands you had, you finish it there, and then next line you come and you start this. See, this is your original command with all the PCH, color and everything, and you closed your parenthesis at the end of it. No, just for the absolute line only you have to do that. There are some other cases, I will tell you when to do that when it comes. Okay. So when you are setting up absolute line, you have to do that. So you close the parenthesis and then come to the next line and set up the absolute line with that. So we did this with the vertical line. And we can actually do the same thing for horizontal line too. See? Oh. No. Okay. Okay. So this is for the horizontal line. Huh? So basically what we did for the absolute line, instead of V, now we have H as an argument. And then we can also combine both of them together. We can actually say absolute line V is equal to whatever number we want, then comma H is equal to whatever number we want, and then we can give the colors also, like each one of one then can be individual colors or one color or something like that. Okay? Everybody is fine with drawing those absolute lines. So you can actually enrich your graph, say like what is your cutoff point, and you can put those lines and you can put them under different colors. So your dots are red, then you can put absolute line in blue or green or purple and make it more fancier. Okay. Even color can be different. So if you are in this case, what I did, I actually when we are plotting vertical line and horizontal line together, I actually did vertical line and horizontal line in two different colors, like red and blue. But you can also say color is equal to red, that means both the lines will be in red, or color is equal to blue, then both the lines will be blue. Okay. I think Francis yesterday showed you this. Now I have to then do this. It's fine. You showed the regression line, so I will find. The one last piece of thing is to show Okay. Okay. So the next piece of thing, that sometime what you want to do in your plot, that you want to actually color plots in plots conditionally, like something greater than twofold you want to show them as in one color versus other color. So you can also do that in base R. Okay, and the idea here is if you actually use this part of the code just where it starts from a plot. I mean, the other thing is actually doing a regression line. I don't want to touch on that now. So we'll discuss what we are doing here. Okay. So up to the first line you are clear. Huh? Everybody is clear about the first line? That plot, we are doing plotting, we are actually taking the object DE and then we are choosing two columns and then we are limited the x axis and y axis to 10,000 and then, so up to that we did. But now what we are planning to do, we are planning to actually change color conditionally, because we are going to give a conditional statement for color. So what is our conditional statement? Conditional statement is color is equal to, so we are defining now color. Okay, color is equal to, so we haven't closed our real parenthesis yet. So we are saying color is equal to if else, this is a command for the conditionality, that absolute value of this column DE obese sedentary column is greater than 2000. That means I am just saying any value you can give. I am saying like if that particular column, any data point which has value greater than 2000 and absolute DE base mean value greater than 2000. So these two columns, I can even use one column also, but I am saying if both the columns, the data point has value more than 2000, then color it as red. Other color it as red. That is what actually I am just telling it. So I am defining the color using that, and then I am just kind of giving. So remove this absolute line thing. We don't need that at this point. We don't want to make it more complicated at this point. So otherwise, so I mentioned that okay, if else, if the values are greater than 2000, then make it red. Otherwise, comma, it should be black, or you can say blue or green, anything. So what I am saying, if the values for both the columns in that data point is more than 2000, then make it red. Otherwise, let it be black. And I am also using another command called as main, but let's forget about it. You just delete that. It doesn't matter. Yeah. Okay. So if you run this, see what is happening. Okay. Now see, this we did for color, but if same thing if you do for shape, you can actually say that, say if I go here and instead of color, if I say PCH and I instead of red I will say 1 or 7 some shape, and second shape is 19. See now it's all black color, but then shapes are different. Okay. Okay. So basically using if else statement, you can give a conditionality and define color, define shape, and you can define both also. So basically you can copy this color is equal to, and then you can actually also define both the statements here. Okay. So PCH we are using for the shape, so we give the two shapes for that, and then so you can use if else statement for this. Everybody is fine with this? What about you guys? Everybody fine? Okay. Great. Okay. So basically this part of the code will give you how to do the shape and color together. So now you know the basic idea that how you can do this conditionally. Okay, so I'm not going that there. Huh? Okay. So okay, there are other blocks of code. Okay. So there are other blocks of code if you see, and it is actually giving you sense like how you can add x labels on x-axis, y-axis, main text and everything. So you can just play with those things. Okay. Now come all the way down to plotting a density plot. Okay, you know what is a density plot? What is a density plot? Yeah, it's basically a frequency distribution, a line plot of the frequency distribution, cumulative frequency distribution. That actually the right word is that. It's a distribution of cumulative frequency. So basically what happens, you have like a series of, say you have, one of the best example of density plot is, no, it's not cumulative frequency, it's a frequency distribution. Density plots are like that. So I actually, one of my problem was that none of our data will give you a beautiful looking density plot. So what we are going to do, we are actually creating an artificial data for that. So artificial data, you just copy this line of code and I will tell you what I am doing here, okay, and then copy here. Okay. So the first two line of codes have nothing to do with any data. What we are exactly doing, we are actually creating some random data. Okay. So what I am doing, I am telling R to do, create 500 random values and store that as an object X. Okay. And the distribution of that data, like the random values those are selected, should be normally distributed, because I want to show the normal distribution, so that looks good. So, and the same thing I'm asking that give me another 500 random numbers and store that as an object Y. So X object X, I will have 500 values, random values which are normally distributed, as well as Y I will have. And then what I am doing, I am actually using plot function. At this point I am saying, if you just do plot X comma Y, why don't you do that? You see what you are going to get. If you do plot X Y, no, because actually that object, if I put, I won't get a beautiful plot. Just for the aesthetic purpose, because I was teaching, I wanted to actually show some overlaps and those kind of stuff. So say plot X. It won't work, no? Yeah, scatter plot you will get. So it's just give you a scatter plot. But what we are looking for is that we want a density plot for this. So then we have to define that the plot function need to plot density rather than, so plot density and then you define the object. Okay. So you plot parenthesis density, then within parenthesis you define the object, then parenthesis you close them. Okay. And once you do that, then you will end up getting a density plot like this. So this is a normally distributed function of X. Okay. Everybody got a density plot? So one thing that you should actually, I don't know whether you noticed it. Yeah. So yeah. And why it is, so everybody will get a different plot. Why everybody will get a different plot? Because you have generated random numbers. Okay, each of us. So if I have to create a same plot for everybody, what I will do? Yeah, so if I have to generate, if I have to tell all of you to generate the same random number, and then what I should, because we use this one and then everybody got different plots, everybody got a different random number. So if I have to generate a same random number for everybody, what I will do? So you use a, set a seed. So if there's a command called as seed. If you say seed is equal to some number, like say seed is equal to 120, and if we are using seed is equal to 120, every one of us, we will get the same set of norm. So what is really happening? Why we get a different? Yeah, we can try that. We can try that. So seed is equal to 120.
It's not seed, it's parentheses.
Oh, seed. Oh, sorry. Sorry. Oh, it's a R. Sorry. CAD is actually, I think. No, S. I haven't used this function from some. Really?
Oh, set.seed,
Set.seed. Set dot. Yeah, some of these functions you don't use often. So this is the command set.seed, and then you say 120.
Can I add something?
Yeah.
So actually this is really important because some analysis you're going to be doing in R, you do maps, you do maps, etc. They use a random seed. So if you, let's say you choose the problem one day, come back and run it again, if the plots may change slightly, you say why that happened? Because it generally starts with a random starting point. If you don't set the seed and you repeat the analysis, that starting point is going to change. Sometimes you get a slightly different plot. So it's not a bad idea to set it up. Always you do an analysis at the beginning of R, you set it up at some number that you always use. In case you need to repeat, or at some point in your analysis, you're doing something that generates some random starting point. Something that I forget often.
Yeah, and especially this is very important for single cell analysis. You have to be really doing it because TSNE plots and UMAP plots are very sensitive to, and they will change each time. And then PIs will ask like, why last time I had something looking like this, now it is looking like that. So why it is so? So one of the practices is to always set up a seed and then keep a number that you like always.
Standard deviation or
No, it's actually. Yeah, the first thing, like like when you go out from home and you cross a temple, you put a coin like that. So it's like that. Or you put a coin, set dot seed, and then you start. So that. Francis, do you want to explain what this seed does?
No, it's me.
So a computer scientist can tell you better than I do. But the random generators uses a seed to generate that number, random number, right? So you can set the specific number for the random generator.
No, even for a single cell, and it's good. Any R code, you start with a seed and then do it.
Define the number. Number, how do you say?
Anything. Yeah, it just means like you are, but that is the number you should use always. That is it. Something. Okay, everybody is fine up to this. Everybody got density plot. You will be able to draw the density plots when you go back. Okay, so now. So same thing like what we did with so what we did with our plot function. Okay, we want to now set up few things. We want to set an absolute line for that. So same way like what we did with the plot, we use ab line function and then.
Why does the appline command not be on the second line? It doesn't work into the same line.
No, it is actually. Yeah, no.
No, I mean there are two separate commands. One is the plot and the other is adding.
It's like line one becomes one line.
So whatever the functions that are being called by the plot function, that needs to be with the plot. And absolute line is a different command, so that actually goes as a separate line. So anytime you add a different command, that will go as a different lines.
So commands function use a different line.
Yeah.
What I guess is a bit weird is that in R, you use two different commands to work in the same plot. That sounds weird. Some languages usually do that. So it could be part of a parameter or modifying the first line. In this case, R knows you plot something before, and you added something to the plot that you did before. That's what is a bit weird.
Okay. So everybody fine. So this is same thing what we did with our plot. Okay. So we are not going to spend a lot of time on this. So we just said you can also do the vertical line, horizontal line. You can add both the lines, and the two more commands. This actually is there in the original text that I have added, which is called as X lab and Y lab. So basically, this is for labeling your X axis and Y axis. So whatever name you want to give to your X axis, you can give that within the quotes, and for the Y lab. And there is another function which people use called as main. So main is for the, if you want to have a header for the plot, you can say main is equal to, within the quotes, you can actually give the name of that plot. So you can use X lab, Y lab, and main, three different syntax for your defining your X axis, Y axis, and the main header of your plot. Okay. So you can try other part of this plots, like you can do X. So also you can actually set like both the sides of this. So there basically you are defining using this C option where you are combining the value. You are saying like from minus, the first line should be on -2. I want a vertical line, but I don't need two vertical lines. The first line will be at -2 and second one is at 2. So that means it will put two vertical lines there. So you can do same thing for horizontal line. And the way it is done, you actually add C, and then within the parenthesis you give the range which you want to define.
What you written in warning is also part of the command?
No, it's actually when running it is coming some of this. I was actually using a command called as add, and it's in the old R version the add was there, and I think it's not there now, so that is why it is showing.
Whatever you've written is not the entire command, like warning.
It's just a warning, don't worry. Okay, now you should not blame me that I actually made you to make a second object Y for no reason. And I just wasted your time by typing one extra line. So what I was actually thinking when sometime what happens, you need to put more than one density plot in single plot. Like you have say one experiment and you have the second one you have. So think about like we have two different data set, one is X, or two different columns, like one is X and there's a Y column. And then, so for that what we do, so copy this part of the command, which is this one. I think you will also get the warning that add is equal to not true, but let's be like that. So what you are doing, the first part of the command, everything is actually, you are aware of every part of it, okay. The only thing that you don't know is this. There is a syntax of LWD, okay. It actually stands for line width. So the line width, you can actually define line width between 1 to 4 in R. So the maximum is 4, the minimum is 1. I think default is 1, but you can actually change that to up to 4. So yeah, it's the thickness of the line will increase, okay. So I want it to be 2, so I just set it at 2. So that is there. Now I want to add my next, I want to overlay my next data over the top of my original density plot. For that, on the second line, I started from the second line, so I closed my parenthesis, and for the second line I said lines. So I actually want next lines, and that also should be density plot, okay. And where the data will come from, it will come from Y, and I defined a new color for that. So original was red, now I want blue one there, and I defined my width of my width of my line, and then there's a command called as add is equal to true. But sometimes this gives a warning, but I don't know whether we are going to get a warning for this time. Okay, we got a warning. But anyway, that is fine. So, but still, warning is not an error. So there is a difference between warning and error in R. When you say warning, it is just a warning that I gave you a warning, don't do it again, and you can still do it and then still you'll get a warning, okay. So it doesn't mean anything, okay. But then one other thing you have noticed it, that I'm actually getting my blue line is actually out of my box. And why that is happening? Because my y-axis is defined by my first data set. Whatever is my first data set, unless I tell that if I actually say the y, if I use limit functions like lim function and limit that, it will be limiting to that threshold. Otherwise, it will use the threshold of my first data, whatever I am giving, first column, whatever I am plotting. In this case, it is plotting y first, and then so what it is doing, that it is plotting x first, and then it is that plot over that plot, it is adding the second plot. So already x and y axis is defined. So that means only whatever leftover space is there, that the second data needs to go. Okay. So there are two ways to deal with this situation. One is you flip the data, you plot y first and then x later on. So that means y will take the maximum value will take, or you use x limit function and then you can plot it. And you can use absolute line and all those things there. Okay. Everybody could make histogram, merge them together. Can do that? Fine. All are expert now in R plotting. Eh? I want you all to use it, okay? It's not like, now we can also do histograms. So we are using same data set, and histogram, so for instead of plot, if you use hist function, HIST, hist function, so same thing, like you are saying x, then you are defining using main, you are defining what is the plot header should be, x label you are defining the label of the x, and y you are defining the label of y, okay. And if you say it, if you run it, you will get a beautiful histogram like this. See, don't you like this histogram? Everybody got histogram? So if we need to add, if we want to overlay a histogram, we overlaid density plot, but if you want to overlay histogram, we need to actually do the same thing what we did with the but instead of line function, line we use lines, we will be using hist again. So basically we are saying histogram, x, color and all these things, and then we are saying y, color, add to t, and then we are just running. So it will overlay our histogram. But what is the problem with this histogram? We can't see. Okay. So what we will do? How many of you? No, change. But that is the reason. No, no reason why you are not seeing it, not because of a color. That is how many of you actually worked with Photoshop or Illustrator? What is actually the word that you use? It's actually called, no, so layers are there, but so two layers. So basically you are putting two layers, but why we are not? So okay, let me ask some other question. Like if suppose if I actually put a very light color there, say yellow, or very light color, will I see the red? So why we won't see it?
We need two lines actually, x की दो lines चाहिए.
नहीं, I want actually to overlay, and I want to see both the histogram clear to me, visible to me. So I know what you are saying. I don't want to use that word what you are using. Transparency. Basically, what is both the objects are actually at this point at 100% opacity. So both the layers are at 100%. If we actually change opacity of, or we increase the transparency of the layer that is on the top of it, the top layer which is the blue one, then we will be able to achieve this by. So the way this is done, it is called as the way it is done called as alpha value. Okay. So if we define the opacity, that means what we are saying, that if we say alpha and then we are defining the color and then we are giving a number should be between 0 to 1, and we, yeah, 0 to 1. So basically if we are saying 0.2, that means we are talking about 20% opacity and 80% transparency. So if you run this now, you will see that your layer is now transparent. See, नहीं वो 3 कलर इसलिए है कि जहाँ मर्ज कर रहा है दैट इज गिविंग यू ए डिफरेंट कलर, and then wherever you have the unique you are getting the unique. Yeah, okay. So to set transparency along with the color argument you can give alpha and then you set the transparency level, and you can actually try with different transparency level like 0.2, 0.3, 0.4, and you will see as you increase the value to 1 you start seeing it like you won't be able to see the other one, and you see it merging. Okay. Okay. Now okay. Now how many of you are actually familiar with box plot? Yeah, box and whisker plot. You want to explain box and whisker plot? Oh, okay. You explain like all the median. Oh, okay, great. Okay. Oh, where I was? I'm a bad listener then, you know. Okay. So again, the only reason why I'm using our XY data because they look beautiful. You can actually use your original data to make a box and whisker plot. So box plot like histogram, you don't have to like again just change the command to box plot and define your x-axis and y-axis, and then you do everything else is like same. But I actually want to first delete something and then I want you to try differently. So let's delete this thing called as notch. Notch, the last notch is equal to t. That one I want you to delete and run this block of code. Okay. You like your box plot? Okay. Everybody got box plot? Now I actually want you to do the notch is equal to true or notch is equal to t. हो गया? Guys, everybody? Okay. Now, tell me what is the difference between these two box plots? There is a notch, like, huh? But why you need a notch? Or what?
Accentuate the median.
Huh?
Accentuated the median in this.
No, but then why actually? What is the use of it?
Get an hourglass figure.
I wanted to be aesthetic, but not that much.
To make it more
No,
visualized.
actually, this is a very crude way to show significance or statistical significance of a data within a box plot. So basically, if you look at notch, and if both the notches are actually same, like or the same level, that means if you do any kind of statistical test, most probably that data will not be statistically significant. But if actually the level of notch is actually, you know, up or down, that actually suggests that the distribution is statistically significantly different. So it's also a kind of indirect statistical test, but
But that is visible.
For the boxes, in the first figure you can't see a lot of difference, but when you do a notch, you feel that the second one is slightly lower.
yeah, but it needs to be a little more lower than that to make sense. But again, the idea is that using a notch function sometimes will allow you to look at the data and say like, okay, this seems like this is statistically significant. But again, statistical significance needs always to be tested, and you need to generate a p-value, and you should report the p-value for the statistical test. But notch will give you a visual sense of that, and then you put a p-value over top of it, it will actually make it more palatable. Okay.
That visual is even coming without even notch.
Not with many data, actually some data, and actually other thing is like if you are using a notch, then those who are aware of box plots, they will see that difference. Even the big differences also showing with a notch will actually will help. Okay. Okay. Now don't look at the code. Don't Nobody should look at the code. I want you to store your obese secondary filtered, versus filtered versus lean sedentary filtered DE table all dot genes. There's a file there, all dot genes file. I want you to save that file as an object in your R workspace without looking at code, and save that as an object name all, AALL all. So that is your second file, the second obese file that you have. I want you to save that file as all, an object called as all, 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 all in small letters, all. Yeah. So this is a CSV file. Use command accordingly, and then store them as. Okay. Everybody could do that. Yeah.
Try to read the file.
Eh?
I have to try to read the file.
Yeah. Okay.
What file I mean?
Uh, this one.
What? Okay.
Yeah. All.
Can I show you a trick? So, I mean, to save us time, computer scientists they're smart. So instead of typing anything, because this is a long file, right? It's called super long. It's quite common that when you start typing something, command functions, name of functions, or something like that, you can press stop, right? Stop away. And you get a list. So I start typing read. Press stop gives me options. Say, okay, I know that it's CSV in this case. Now I know that I need to give it a file name, right? That goes in quotes. So if I press stop, it's smart and saying, okay, I know you want to load a file. So it's giving me what is in the browser, right? So if I scroll down, it's going for home, and you have it. And you don't have to type, you can paste on it. And then now, can I finish on what?
Yeah.
So cloud is your friend for a lot of things. So you were asking why plot knows that x is x and y is y, right? So when you do plot, or any function also that's true for another language, we call it functions. We're calling a function called plot. Sometimes expect what we call positional arguments, right? So plot expects to be the first argument in x and the second argument in y. But if you want, you can be really explicit what you want. You can say, so if you press stop, it's giving me what options do I have with the top? I have x. So give me x. So I'll give you whatever was x. I don't remember how we call it. So now you know the the stop, I want to give you more arguments, I know give me y. So you can be really explicit if you want. You don't have to trust that positional argument. But it's true that a lot of functions in R, especially the first argument tends to be really positional, and you can save time and say object equal and give the object name. You don't have to. But yeah, if you want to be really explicit, you can be really explicit. And that, the stop is always with that, right? You can do autocomplete with that. And that's true for a lot of IDEs.
Okay. So everybody got the all object? Eh? Okay. So now what we are going to do, we are actually just going to plot this, just plot this, and let me talk about this plot. So this is what it is. It is actually a 2D scatter plot. Is that right? Eh? So what are we doing here? Just think for a second before. Eh? We don't have a column name log 10 like. So what we are doing, we are taking the column which calls all, a p value column from the object all, and we are converting each of those value in minus log 10 range. So we are actually logarithmically transforming those values. So why we are doing this? Anybody can tell me what I am trying to do?
You're matching the scales.
So there are two things there. Eh?
P value
No, what I am
can be-
actually,
P value can be very varied.
Pick the p value from the same file.
so once you actually convert a value into log scale, you are basically making it into a linear scale. Okay, and that is what I am doing. Why? But why I am doing that here? Why I need to actually change my p value into that? Because I am trying to make a plot which is called as volcano plot. And for RNA-seq, volcano plot, you have seen like everybody showing the volcano plot. So on the x-axis of a volcano plot is log 2 value, and y-axis is a p value of. So what I want you to do, delete this minus log 10, okay, and then remove this one set of parentheses from there. Just you all underscore p value, and see how it looks like, what our plot look like. Okay. See, do you like this plot? Is it look like a volcano plot? No. So if I transform this, eh? No, it is called as volcano plots. Basically,
We are getting error.
Show the previous command where you removed minus log 10. Just
oh, so I think you might be struggling with parentheses. So just use the plot, the way you plot, the scatter plot. Forget about what else you are doing. You want to plot two columns, the p value column and the fall to change. That's it. That's the first thing I want you to do. I will finish with this in like in another 5 minutes, and then you will start with the experimental design. So you can start your laptop. Yeah, no, this was you will start with the experimental design, and then yeah. Okay. Everybody could get the so why it is called as volcano plot. So how the lava goes, you have seen that how the lava comes out of the volcano. So is that not looking like that? It looks like a volcano is erupting and all these things are going up. Okay. So, yeah, okay. Everybody got your volcano plot? What about people there in the back? You got? तुम नहीं कर रही हो ऐसे बैठ कर अच्छा नहीं नहीं ठीक है ओके ठीक है okay so as usual you can beautify this plot a little bit. So the first thing what I want So you can look at the rest of the tutorial. There are things that you can do. It's basically the same, the plot function what we see. We are just using them on a log transform p-value to get different ways of doing it plot. And then you can also use if else function like this. See, so you can actually the same way like what we were using if else function. You remember like previously we were coloring under using a different conditions. So you can do those kind of coloration. You can add labels. So it's same like what you do with the plot. Whatever you did with the plot, it is same. But the difference between normal plot and the volcano plot is the normal plot is usually anything you can plot on an x and y axis for the normal scatter plot. But technically, always volcano plot is about log 2 fold change and the p-value, and p-value is in a log axis. So that is log 10, not the natural log. So this is something that you should be aware of, and volcano plot is a very interesting tool that in most of the RNA-seq paper you have to make it, unfortunately or fortunately, but this plot means nothing. End of the day you have to show this. Okay, so this is a good tool, and I hope I'm actually stopping at this point here. So I hope what you learned now in like last 1.5 hour that how to actually handle data in R and how to check your data. So basically you will be using head, you will be using dim, using your tail, you can use str. Then what are the objects you actually stored in the in the workspace? You can see that using ls, and then you can use plot, density plot, or histogram, or even the all these things. You can conditionally color them. You can add text into it. All these things you can do using R. Now, this will bring me to the final closing statement, which is you don't have to always wait for genomics data to practice your R. On a day-to-day basis, even if you are generating small data, okay, like 10 line, 20 line data, you want to plot, you want to make a histogram, you want to make a line plot, you want to make a scatter plot, use R. That will put you in touch with these tools. You will never forget it, and when time comes, then you can actually use. And these plots are actually beautiful also. You can do, Excel has like limited ability to modify, but here you can actually modify. There's no limit for modifying the plots. You can do all kind of creative things on this. So on a day-to-day basis also, even if you are budgeting or you want to get a plot, you are actually anything you are doing, use it. And so that will keep you in, you keep practicing it, and that is how you will be. And then when time comes for genomics, you will be definitely, it will be easy for you to do.
So one more thing. So visualization, right? Or check if your object exists. There were some errors here that you have to solve just checking. Did I actually create the object? Was the object there or not? So just check it. So I don't think you're going to use this much, but in R, right? So there are a couple of things you can do. You don't know what function
One
does,
thing,
right? Like
Francis, one thing I want you to show, I don't know how to do that. Like you make a plot and how you download the plot in Jupyter Notebook. Just show them that you made a plot and how you do that. Okay, just one thing I forgot.
No, but they're going to do it.
Eh?
They're going to do it all the time tomorrow. Or today, this afternoon, they're going to do it.
Oh, downloading that.
Yeah,
Okay,
yeah.
so the plot that you made, how to download it from the Jupyter Notebook.
So you don't know how plot works, right? So if you do question mark plot, you're going to get a help. Normally, if that function has a help, you will get it on the screen. And it tells you what x and y is, type, all the arguments that you can use in that function. I don't think it's that useful because at the end of the day, probably you prefer to use Google. You're going to get an output that is nice. It's not really useful. You can also type help. I think help. Help, no, but help, I don't know what it's going to do, but help should produce the same output. Yeah, it does. So that's your job. The question mark. I think that's it.
Yeah. Okay.
But yeah, but that idea that visualizing whatever you're creating, checking if it exists, we do that all the time. Like when you find two files, sometimes Can I? All right. Still doesn't work.
So I just actually wanted to just one point. See, the same set of commands, same way. Actually, you can use this in RStudio. So if you are actually running RStudio and that is what you are comfortable with, just use that in Jupyter Notebook.
Yeah, I mean, Jupyter Notebook is not a language. It's just what we call IDEs. So RStudio is an IDE, Jupyter Notebook is an IDE. They don't, R is the language. So whatever you're typing is just R. You can use it in any IDE. Visual Studio probably.
The workshop, does the ID, the notebook stay with them or is it just for the workshop?
So the Jupyter Notebooks, I can send it to you if you want to, and you can use them in your own installation. But that, so the Jupyter, what we're using is Jupyter App in AWS. That is going to be gone.
No, but their Jupyter accounts will be there or
No, no, they're not going to be there. So the way to use,
can they separately make Jupyter notebooks for themselves?
yeah, they can do it in your own laptop. Yes, yeah. You can download. So Conda and Jupyter Notebooks generally work together and work well. I recommend to work with both of them. So if you Google how to install Jupyter Notebook, probably you're going to get instructions how to use Conda too. I don't know in Windows. I'm not an expert in Windows, so I don't know exactly how Windows works. But I'm assuming it's going to be something similar. I would recommend to work with both of them. So Conda and Jupyter Notebooks. And if we have time, I can prepare a short way, an explanation how to do it. We can do it together, but I mean, it's not that complicated. So you can have your own Jupyter lab, actually it's called Jupyter Lab, running in your own computer. So everybody unwind a little bit. Yep, good. So for the next 2 days and a half, we're going to be working with transcriptomics, and Bonnie already started talking about it during his presentation. So we wanted to talk a little bit about experimental design, right? Actually, this talk started when somebody asked me, why you don't give a talk about the principle or the main problems you encounter when you deal with biologists, right? The communication between a biologist and a bioinformatician. So what is happening there, right? What are the main problems that you encounter in these situations? So I ended up, I started preparing the talk and I realized I only have one slide. So there was only one slide. So there's only one main problem that I have with, let's say, people that comes to us to do NGS, right? And I'll tell you later what it is during the presentation. Then it evolves to be, okay, what are the experimental design considerations we need to have when you do an NGS experiment? So the focus, though, is going to be for transcriptomics. Whatever I'm talking here is going to be about bulk RNA-seq. But you probably can extrapolate a lot of things we talk to any other type of sequencing. I'm always jealous when somebody finds a really cool quote on the presentations, and I'm not that cool, so I never find one really cool. So I found one, but then I realized it's not nice. So can I put it in Latin so it looks even cooler, right? Anybody can guess what it says here? Yeah, you said it right. So
Bag out, garbage in, garbage.
yeah, exactly. Garbage in, garbage out, right? So that's the main issue. If you don't do a good experimental design, what you're going to get? Garbage, right? So we need to define some goals here. Is basically what are the main problems we find bioinformatician teams we encounter with doing experimental design and how we deal with them, or things that we need to think about it when you do the experiment, right? So a lot of biologists, when they come to us to the Genome Center, they think, okay, I need to do transcriptomics, so let me send the samples and they figure out everything else, and I'm going to get something out of it. So again, I already said those things, right? Basically, we're going to be working as an example is going to be bulk RNA-seq, but you can apply it to other type of sequencing. It's not only exclusive for this necessarily. Also through this, we're going to learn a few concepts you already know about NGS, but also about data analysis, and we will call exploration data analysis, which is important. You already did exploration data analysis now, right? You printed your table, you created a plot. That's what sometimes we need to do, just explore the data without coming up with any conclusions necessarily. And again, this is what I said before, right? Anything you learn through the workshop can be used to communicate with, if it's not you doing the analysis, whatever analysis you have that is going to be doing it. Hey, it's working now. What's going on? Actually, go to the first time it's actually working, right? Yes, it seems that it's going. Do you mind to try? So go to that website that we use that is called paulev.com. If you start typing it in your browser, it's going to autocomplete probably, right? I'm hoping it is working. This morning wasn't. Okay, it's asking you, but I don't know if it's going to be live. That's what I'm worried. Can you try to type something and see if it shows live? So some people already answered? Okay, I'll read them. So reproducible results, right? Meaningful data are some of the answers. Anything else? Why we should bother about having a good experimental design? So one is clear, reproduce the data. That sounds good. So definitely it's not working. Okay, we have more now. Ooh, remember, don't use white spaces because I'm not going to be able to read it. Because I'm only reading data now, basically. It's the most popular answer. I guess it's meaningful data, good information, structured data. Don't use white spaces because it's not going to work. Okay, we have more. Garbage in, garbage out, okay. Comprehensive results. Okay, everything is about the data. Okay, that sounds good. So you see this ugly slide that I did here? So I start typing in and I think, oh, this is too ugly. So that's why I put the question. I thought I would resource all the answers from you. And pretty much you said everything, right? Obtain meaningful results, improve the quality and validity of the science. Nobody mentioned that one, though. Save time and money, right? And that's very important for us, too, save time and money. If garbage in, garbage out, I'm wasting my time doing an analysis that I'm giving garbage out, right? Oh, yes, and another one that sometimes we forget, higher impact factor in the journal, right, that we are applying to. And I was looking, when I was doing all these slides, I was looking, can I find an example of a failure in experimental design in NGS? I couldn't find any, right, because everything you see published is being through a process of peer review, so it's going to be hard, you're going to find a failure. But you can find some examples still. So this paper is not NGS, but it's a GWAS, which is close relative, right? So what they did, it was an analysis of people, right? They have a GWAS study where they found 150 SNPs that were able to use to predict if the person would be really old. And they say they were able to predict it with 70% of accuracy. It was published in Science, so a pretty good journal, right? But somebody started getting the data and doing analysis, and they realized there's something wrong here. So what they did, what happened was that they decided what they did was to use different SNP arrays for the young people and the old people. So what they saw was an artifact produced by the microarrays being different, right? So if you have done a good experimental design, you should know that you shouldn't use different technologies or different type of microarrays to do this type of analysis. So I was able to find one of the responses of Science, and basically they asked them, oh, can redo the analysis and see if this is still truth? And Science replied saying, no, the data, even after doing the reanalysis, we cannot accept that this is in time. So, yeah, it was retracted basically because the experimental design wasn't good. So they were using two SNP arrays, one for the young people, one for the old people. So the difference they saw was the microarray. So the type of microarray they were using, it was different. They couldn't compare it because the difference they observed was artifacts.
But how did it make it to Science in the first place?
Oh, because they didn't notice that there were two different microarrays. Science, or the peer reviews went through it, and it was other people who got the data, reanalyzed it, and they realized they're using two different microarrays. I don't know the details of how they...
How did it miss the first peer review?
Most of the time methods.
Methods are, yeah, what happens...
How did it in Science?
No, I mean, reviewers are saying everything.
It went through Science,
All
definitely.
the reviewers were friends. The first set of reviewers were friends.
Probably, and the third review never existed. Okay, going back. So we talk about the central dogma. We said we're going to talk about transcriptomics and the applications of RNA-seq, right? Generally, when we talk about RNA-seq, we use it for different applications. Oh, come on. Here we go. Okay, this is... Yeah, so we can use it for discovering novel transcripts. We can use it for de novo transcriptome assembly. So we have a species that we don't have a genome as a reference. We can do, or we need the transcriptome. We can use it for do a de novo transcriptome assembly. If you care about the sequencing, maybe you can do even a SNP discovery. Maybe it's not the best strategy, right? But we can use it. Or we can use it for differential gene expression. That's probably the first thought that you have in mind when you do RNA-seq, right? And generally, when we do that, what we're doing is comparing something with something, right? You may have a control, you may have a mouse control, and then you have some phenotype, and you want to know, okay, what are the causes of that phenotype, right? And most of the time, what we do is using the RNA as a proxy about what is being expressed, what are the proteins being expressed. I think we all know this. Bonnie also talked about how we do bulk RNA-seq library preparations, but that's the main idea, right? That definitely different steps through the process, creating the ctDNA, removing any contaminant DNA. We've removed the ribosomal RNA using two different strategies, what he said, like ribosomal depletion or using the poly-A tail. We fragment the RNA. Sorry, I forgot it was. The reverse transcribe happens later. Ligate the adapters, size selection. I think, Bonnie, you went all over this, right?
Yeah, I just want to add actually one more thing, which I actually forgot to mention. Because we never thought that. Okay. So, fragmentation. DNA fragmentation is actually straightforward. That you can fragment DNA, and there's no intermediate step there. But the RNA fragmentation, there is a issue there actually. So there are two places that you can do fragmentation. Either you can fragment RNA itself, or you can fragment cDNA. So like in case of this picture, Francis is actually fragmenting RNA here, and then but there is actually you can also fragment cDNA. Why this is actually important, or is it important at all?
If you want to see the epitranscript from this.
No, it's not epitranscript. It's about just RNA. Okay, so earlier days when I was fairly young.
Oof. When he started talking like this, it's going to be a long story.
It's not long. It's actually long story short. So when fairly I was young, then one of the key challenge in reverse transcription was to create a full-length RNA, cDNA. And they, in 2005, I think 2005, I was still young at that time. So 2005, Frontech came with a technology called as template switching. And that template switching is actually now used in every single cDNA, in every single cell RNA sequence. What actually does that you actually create the first template strand, and when the strand ends, it adds an extra GG. So polymerase will add an extra GG, and then you prime your second strand from that. And then so that's why every single cDNA, double-stranded cDNA that you created is a full-length CDNA, and this strategy is called as template switching. Why this is important? Because before this strategy, when you do fragmentation of cDNA, instead of RNA, if you are fragmenting cDNA, then you have a mixture of cDNA with various sizes, because now all the cDNAs are not full length cDNA. Okay, so you will get all these things, and then end of the day, what you will get a biased library. Either it will have a 5' bias or a 3' bias based on what kind of library you are preparing. So, but since the template switching chemistry came, after that we are always making full length RNA. So it doesn't matter that whether we are fragmenting RNA or we are fragmenting cDNA. Okay, so now in all the protocols, they are using TSO template switching oligo. So that's where it doesn't matter. But there was a time, almost like 5-6 years back, when template switching oligos were not that common. Then it was important that you fragment RNA rather than fragment cDNA. Okay.
Oh, sorry. Yeah, the last step, right? We have our FASTQ files, read 1, read 2. Nowadays we do both. In the past, with one was enough, and actually we can talk about that if we need to do both of them or not. So once we have the sequences of the files, of the FASTQ files, what do we do with them? Yeah, that's a good thing. We can do FastQC, the QC part of it, and filtering that we already talked a little bit. But now you have multiple options when we talk about alignment, right? So depending on how much information you have about your genome. So if you have a genome reference, right, you have the option of mapping directly to the genome. That would be the first option here. You could, if you don't have a genome but you have the transcriptome, you can map directly to the transcriptome. Or if you don't have neither of those, you could create your own transcriptome and then map it to that transcriptome. There's a big difference, though, between these two ways to do the alignment, right? If we map to the transcriptome, there's no splice sites, so we can map our reads directly. But if we map to the genome, we can have reads that map in exon 1, and the same read, a fragment mapping to the exon 2. So it's being spliced. If we try to map it to the genome, it's going to be really hard because you have an intron in the middle. So the way to do it is using specific alignments that are called splice-aware alignments.
So if you're looking at splice site variants, I mean the effect of a splice site variant, you would have to align it to the genome.
Yep.
If you're looking whether a splice site variant is causing a change in the transcription,
Yep.
you would have to align it to the genome.
Yep. So in case that the exon get extended naturally. Yep.
Because generally we do RNA-seq to look at to look at transcripts, but you can also use it to look at the effect of splice site variants.
Yep. Or the creation of new exons or whatever. Yeah. Yeah. There are even a quasi-aligners that we are not a talk here, but yeah, let's not talk about them. For now, we're going to talk about two types, right? Which is aligning directly to a transcriptome, that is a classical aligner that you can imagine, taking the read and mapping the whole read however you can, or using the splice-aware alignments. In bulk RNA-seq, there's a step of quantification, because we don't care about the sequence anymore, right? We care about counting how many times we see a transcript in our cell or in our tissue or whatever sample we have. So we need to quantify. So if I see 2 sequence mapping in gene X, it means that I have 2 quantification of that gene, right? So we need to quantify. After that, we do the differential expression analysis. And after that, we can do even more downstream analysis. And we will talk about them when we start doing those analyses, right? So what we're going to do today is going to be part of this analysis. Let me see if it goes. Okay. So we're going to do between today and tomorrow is going to be this. So we're going to do the QC and filtering. We're going to do the splice-aware alignment, quantification, differential gene expression analysis. And depending the time we have or not, we're going to do what we call pathway analysis or downstream analysis, depending on what we want with it. Actually, this afternoon, the only steps we're going to be doing is these 3 steps. And tomorrow, we're going to focus on this. Okay, but going back to the main idea here, we're talking about experimental design. So our experimental design is assuming one thing, right? So we have, let's say again, two type of samples, right? We have our control and some other sample that we see a phenotype. And we're assuming that the changes that we observe in expression are caused because the condition under study. Maybe we treated with a drug these mice and became a different phenotype, right? So we are assuming that the drug is causing the difference in expression. Is it always true? No. Generally, there are going to be other factors, right? And that's always true. There's always other factors. It's really hard that you're going to get a perfect study. Or it's impossible. You're going to get a perfect study. Generally, you're going to have known factors, right? So if you've been good in the lab, you begin tracking how old is that mice, where was the cage coming from, what temperature was in the room. I don't know if you keep track of that, but if that day rain may be important for you in the experiment or not, or whatever. You're going to keep tracking of a lot of things. But there are a lot of hidden factors, right? Technical variability. I don't know, that mice may be sick, the mouse may be sick for some reason that you don't control, it may be hidden, that information is hidden to you. And of course, other interactions between the environment, epistatics, whatever. There can be other interactions, other things that you don't control. So, right, we said initially, do you remember when we're doing linear regressions, right? We talk about how to formulate it. So it's the same idea. We're saying expression depends on the condition and the study. However, the reality is, yeah, it depends on the condition of the study plus other factors. Then it's not that linear. You have other factors involved in it. It's still linear, but it can be other factors. So through the whole process, right, we have a lot of decisions to make in theory and other steps that can affect those factors I'm talking about that can affect the expression. So platform of choice. I mean, Bonnie has been already talking about platform of choices. Depending on your goal of the experiment, you're going to choose one or another, right? In bulk RNA-seq, currently Illumina is the platform of choice. You only need short fragments. You don't need to worry about long fragments. But if you want to capture the whole transcript, you're going to need to move to probably PacBio, which is going to give you a full transcript, right? Bulk RNA-seq, Illumina is the choice normally. It's what we currently use, or the short read technology. But you need to make a choice, right? Or whatever is available to you. You need to make a choice about, do I want to do poly-A or not? Do I use ribodepletion? We already talked about that. We also talk a little bit about this. I don't know if you remember. You need to make a choice. You're going to do the type of library is going to be unstranded or stranded. We call it direction, or I think, Bonnie, you call it directional library or not directional. Yep. So basically, you keep information about what strand are you actually sequencing. You're going to make decisions about, do you want to do single end or pair end? You want only read one or read two? The read length, we talked already about it. For bulk RNA-seq, short reads works. How much? We can talk about it too later. Depth of sequencing, how much sequencing you're going to need. And can you think of something that is missing here? Maybe when you do bulk RNA-seq, or when you do any kind of quantification studies. Another important decision. And at the beginning I said I could summarize all the problems we have as a bioinformatician with one slide. That's the thing that is missing here.
Non-coding RNA.
No, biological replication. It's something that for whatever reason, a smart scientist in the lab, they do replicates all the time. They come to sequencing, they show up with 1, 2 replicates, and they say, okay, what do you want me to do with this, right? So yeah, so I could have summarized my slide about the problems we encounter just with the bottom one. Because basically all the other options we can figure out, right? We said Illumina machine, we're probably going to prefer poly-A if you only study protein coding genes, right? Library preparations nowadays, I think the only thing we do is a stranded because it's the same price. Why not to use it? Same things for the rest, but biological replicate always comes from the investigator who needs to be smart about it. So we already talked about this, right? Currently nowadays, we don't have to think too much about the experimental design, about the platform. They give us cheap options. You're going to go for the cheapest one. But in the past, even the flow cells were small enough that we needed to make decisions of how many samples we put per lane, because there were some variation between lanes, and you want to control for that technical variation. Bonnie already showed the ones that we have available, and depending on your decisions. This one, I'm going to insist a little bit, right? It's depending on your goal, you may choose poly-A selection or ribosomal depletion. Generally, poly-A selection is the one of choice, but if you care about non-coding long RNAs, then you're probably going to need ribosomal depletion because not all of them have poly-A tails. There's also a difference between price. Generally, FFP is going to be lower quality. Ribosomal depletion is going to be better in those cases. There's exceptions for everything here, right? But those are general decisions you need to make. Okay, so if we...
I have a question, but if you want to do only microRNA or small RNA, you can also size select them.
Yep, yeah, that's true. So that's a good point. So for, if you remember in the slide, we're talking about the process. There's a size selection process. For protein coding genes, generally we pick everything that has a fragment that is 100 or above, right? Is 100 the cutoff? But if you want to do small RNAs, you'll throw them away because small RNAs generally are 20. If they're mature RNA, small RNAs are going to be 20 on size, right? So if you throw away everything that is shorter than the 100, you're missing the small RNAs. So in those cases, you can prepare a separate library with the shorter fragments and do a small RNA-seq. Okay, so if we compare the type of poly-A libraries and ribosomal depletion libraries, there's a big difference regarding where they map. When you look at these samples and you look at the depletion ones, you see a big chunk mapping into intronic compared with the poly-A capture. So two questions here. You think we can compare them? So if we do an experiment, somebody comes, oh, I did control samples using poly-A and I use my treatment samples using ribodepletion. Can I compare them? It's going to be too risky, right? There's going to be a lot of difference caused by the technical problem. Sorry? Exactly. So my second question, why do you think we get so many intronic alignment when we use depletion?
Depletion is not absolute, so we have something.
No. So the reason is you capture immature RNAs because they don't have the poly-A yet. So those are still not spliced, so you're capturing transits that have introns, and probably you're sequencing a lot of introns because of that. That's probably the main reason.
Actually, if you're interested only in mRNA and you're using a ribodepletion,
Yeah, but it's really,
you will be,
you're wasting sequencing.
immature RNA also
Yep.
will be sequencing, which will not be able to
Yep.
use that.
So that is why generally we prefer poly-As in those cases, but it's true that when you have a low quality sample, ribosomal depletion can work better, capturing the RNA that you have there. So sometimes you don't have an option.
Formalin fix is ribodepletion better than poly for formalin fix?
Always ribodepletion.
For formalin fix.
Because it's already fragmented RNA and poly-A will be impropriate.
Well, we have a question here that I forgot what it was. Oh, we already know. We were talking about it. And we know it doesn't work, so like the pointer. So stranded and unstranded or directional and non-directional, right? So advantages of directionality. So we talk about what if you have two features that overlap, right? So if you do unidirectional, you're not going to know, or non-directional, you don't know how these read is coming from gene X or gene Y. And there are features in human genomes that still overlap. So that can be a problem. Or antisense RNAs. So if you care about those or you want to know if there's an antisense or not being used or not on your experiment, you're going to have to use directionality. That's why it's important. But I don't know here if whatever you send your samples, they do unstranded or not. In our case, we always do a stranded. It's always worth it to use that information. And you can incorporate that information in your analysis. So you can tell to the software that you use this type of library so it knows that whatever sequence it is, it knows exactly what strand produced it. What about single N and per N, right? That's what we said. You can do just read one and read two. In the past, we only use read one because it's good enough to know what fragment produces. You only need to know where that fragment is coming from. So having read two doesn't mean necessarily you get doubled information. It's not true. You don't get doubled information. Because with read one, it may be enough to know what this fragment is coming from. It's coming from gene X or gene Y. Read one may give you that information already. But still, there's advantages of using parent sequencing, especially in cases that you care about a splicing. So you increase the chances of knowing if an exon exists or not, what transcript produced it, if it was transcript 1 or transcript 2 within the one gene. It's also mapping is going to help, definitely. If you work with transcriptome assemblies, you're going to, and in that case, you're getting double information because you need to assemble it. And Bonnie mentioned already, between single N and parent, the difference in price is so minimal nowadays that parent tends to be the standard. So how long needs to be the read, right? Again, it depends on your goal, the decision. If you care only about gene expression differences, you can do short, right? Do you care about actually differentiate between your isoforms? It needs to be long because you need to be able to differentiate between if the transcript has exon 2 is present or not. You need to increase the chances of reads mapping in exon 2. The longer you read it is, the higher chances are that you're going to be able to differentiate between your isoforms, right? Or the presence or the absence of exons. So depth of sequencing, Bonnie also talked the other day about it, right? So it's quite common we talk when we talk in NGS, and we talk about, oh, my genome is 30x. So 30x means that, what Bonnie was saying, that you sequence that base on average 30 times. It's on average. Doesn't mean you sequence everything 30 times, right? We also talk about breadth of coverage. In that case, we talk, for example, for whole exon sequencing for us, a high-quality whole exon means that, for example, 95% of the exon has been covered at least 10x or at least 20x. So a 30x genome would be at least 50%. Well, if you use the median, it would be at least 50% of the genome has been covered at least 30 times, right? So when we talk about depth of sequencing, how much depth of sequence we need for RNA-seq? Well, it's hard to predict. So you can create some sort of plot, but what we know is the more sequence we add, the more genes we detect. So the more sequence we add, the genes that are lower expressed, we're able to detect them. So the question is, do you care about the lower expressed genes or not, right? So there's a way to figure out if you reach a saturation, meaning the more sequencing we add, we barely detect newer genes. It means the sample is saturated. It's not worth it to add more sequencing because you're not going to detect anything newer. You can do experiments of, oh, this is starting to be annoying. Okay, you can do experiments where you only get a fraction of your files and try to figure out how many genes I detect. You add a little bit more and say, do we see the curve growing? You keep adding, oh, I start to see saturation. Now I know that if I try to sequence more, I'm not going to do get more. Is it worth it to do all this? Probably not, right? The cost of sequence is going so low that probably you can make a decision in advance of saying, pretty much I can know that if I do 30 million reads, I'm going to saturate the sample. Is that true for every organism? No, right? It depends on the organism that you're working. You may need more or less sequencing. It will depend on if you're working with a small organism that only produces 10,000 genes, you know that you're going to get less sequencing than, for example, the human that is going to produce a minimum of 10,000, right? You work with a virus that only have 100 genes, you're going to get less sequencing.
So I couldn't understand this biological replication.
Sorry, what?
What is biological replication?
What is biological? Oh, we can talk about it.
Example, you do it multiple times.
Yep. So I'm specifying biological replicate, meaning we generally don't care about technical replicates, and we talk about now about this. So what we need, why do we need two biological replicates? For any statistical analysis, right? We need to access the variability in the data, right? So if we want to compare are cricket players in India better than UK, right? Well, we know for sure that it's the case. But let's assume that you need to do a study. Are you going to choose one cricket player from England and one cricket player in India and compare them? No, right? You're going to do replication. In that case, it would be biological replication. You need to do, if you're going to do a contest of, how you call the, throwing the ball, I don't know, for example, right? You're going to make them maybe doing 1 time or 2 times, depending on the technical variability that you have. If you know there's going to be a lot of technical variability, you're also going to do technical replicates. in NGS for bulk RNA-seq, the technical variability is so small that you don't care. It's going to be present, but you don't care that much. The important thing is the biological replicates. So in any experiment that you think about, I need to quantify, think about replication, right? So if you think, oh, I'm quantifying this, oh, probably you need replication, right, most likely. But it's true in a lot of experiments we do.
But replication should ensure the data is clean. But why it is causing error? You mentioned a source of
Oh, because people, well, source of errors because people comes to us with just one replicate, and then there's nothing we can do with it. That's what I mean as an error. No, it doesn't cause a bias in the data or not. It causes the bias because you only have one replicate. If you try to compare it, you already have a bias because you only have one replicate, right? Whatever that.
how will it replicate? At least 3.
We can talk about it.
The more the better, but what is the minimum threshold of the biological replicates you would recommend?
Next slide, we can talk. But any questions about this? I think we talk about this to, everybody has this in mind. You do that in the lab. There's no different in NGS. Oh, yes, so you could do a test, right? You could say, let's sample a few samples, let's sequence a few samples and see what happens. And if most of your genes or your replicates have barely variability, small variability, right? You can assume, sorry, I'm losing my voice now. You can assume that you don't need many replicates. But if you have some expression like this, you clearly need, I need more replication because it's going to be really hard to know if these are differentially expressed or not. Do you know that in advance? No. So it's really hard to do. Is it worth it to do some sort of how we call it, a pre-experiment or some test experiment to know how much replicates you need? Maybe it's not worth it, right? Now the question is, how many replicates? We heard 3 over there. Any other numbers? How many replicates do we need?
The more the merrier.
The more the merrier? That's a good answer, yes.
3 to 5.
3 to 5? Can we answer it? No. I mean, a good answer would be the more the merrier. If you have a lot of money, why not, right? 3 to 5, that's what we generally see. There are publications with 2 replicates. I've seen them all the time. I'm never going to recommend 2 replicates, never, ever, right? Yeah, I mean, generally, if somebody comes to me and they don't know what they're expecting, I say minimum 3. But you are limited by the money at some point, right? So you're not going to be able to do as many as you want. There are rules of thumbs that you can apply.
Like if there is a human data, we need more replicates. So if it is mice and the same strain and same condition, then you can do with the 3 to 5.
Okay, here we have a good point, right? So we'll mention it now. So one of them is that this is a rule of thumb. You just created a rule of thumb saying, oh, if it's human data, I'm going to need more replicates. If it's a mice growing in a lab, I may not need that many replicates. Why? Because you control the conditions. So also depends on your goals. Are you exploratory analysis? You may not need that many replicates. You're just exploring, right? So let's see what happens. But you may care about the genes that are highly expressed, and I want to see big differences. Oh, I'm going to need more replicates for that. Do I care about detecting most of the genes that are differentially expressed? Then you need to add more replicates for it, right? So if you care about the ones that are low expressed or the ones that are higher variability, you're going to keep adding. The effect of the treatment is an important one, and people forget about that, right? If you are studying meditation, right? And you're trying to do, so meditation can be complex in the sense, okay, sure, you may have effect, but the effect may be small for some people, right? The effect for other people may be higher. So it's different than treating a mouse in the lab that you knock out a gene, you know that the phenotype is going to be big. So the effect of the treatment is important here, and people tend to forget about that, right? Or, you know, if the treatment is removing the water from a mouse for an hour during a day, you know the mouse is not going to get that much, so the phenotype is going to be small. And the other one we mentioned, this, right? You're growing cells in a plate. You are controlling so much environment in that plate. All the cells are equal. So probably you need less replicate than working in the lab animals, or you're working with wild organisms like humans, that everybody has a different lifestyle. So you already have in mind a little bit of that concept. So years ago, we used to have this type of studies trying to do power calculation. What is better, adding sequencing or replicates, right? Nowadays, sequencing is never a limitation. The limitation is always going to be replicates, or think about replicates. But yeah, we know that replications ended up being what gives you more power. So the pilot studies generally, so this is what we generally recommend, right? So if you think about, you want some general recommendations, is we always say a minimum of 3 or 4 replicates that we should think about it. And they always have money limitations, so they're going to stick with 3 replicates no matter what we tell them, right? And people comes with 2. So, and when they come with 2, we are not going to change their mind because they already give us the samples.
Is it a good idea to have more replicates and maybe a lesser number of reads? Or
Yeah, if you're trying to save money in that sense, yes. Yes, so this is what it's telling you. So less sequencing is, you're not sacrificing that much, but removing a replicate, you may be sacrificing a lot, right?
So does it applicable to any genome?
But it depends on your goals a little bit, again.
So it depends upon any type of sequencing, whether the whole genome, whole exome. If we reduce the
Oh, yeah. I mean, in these cases I'm talking about replicates, I'm talking about quantification studies, right? So if you are trying to do variant calling, replicates are not important in that case, right? Because you only have the samples that you have, so. But anything that you quantifying peaks, chip-seq, all those type of things, you need to think about replication. There's the ENCODE consortium. They publish what they call best practices. They have best practices for RNA-seq, chip-seq. Probably they have other documents where they list what they consider best practices for their project. Not your project, their project. But if you need to check some kind of best practices, you can access those documents. It will give you an idea. Actually, I don't know what they recommend for RNA-seq in number of replications. I don't remember. Who knows? Maybe they recommend 2. Then ignore them. Okay, going back to this idea, right? So we talk about all the decisions you need to make. But is there any way we can test if this is true, or we have other things that are affecting our expression? We can do that. So we can do some QC processes before doing the differential expression that is going to tell us if this is true or not, right? So if we have important factors in our samples or not. So the idea is, can we do any QC telling us if there are good clustering? Are the expectations of the condition being really important in the expression or not? So basically the question of what are the measured sources of variability in the data? So we can do that, definitely. Anyone here knows how we can answer these questions, doing, let's say, a preliminary QC analysis? Did anybody here done RNA-seq analysis before?
the changes in the values of some factors, like we look into the changes in the values, like for the intensity, we talk about the data. So whether they are falling into the similar range, or what are the genes which are different expressed, they are same kind of genes.
Well, that could be a way, I guess. There's a simpler way, though, to that. PCAs? Anybody has done a PCA before? Okay. So
Then they will fall into certain categories, yes.
So a PCA. Did anybody here haven't seen a PCA before?
Yes.
Everybody, yeah, more or less? So basically a PCA, it's what we call a dimension reduction technique. If you work with single-cell RNA-seq, it's called the UMAPs. UMAP is also a dimensional reduction. So basically what you're doing, right? So you're taking a sample, you are measuring 20,000 genes if it's a human sample, right? You have 20,000 variables, 20,000 dimensions. So if you try to figure out if the samples cluster together or not, for example, right? You cannot plot 20 dimensions. You need to work something manageable, right? So that's why we use techniques like principal component analysis, the PCAs, that's what it stands for. It's a dimensional reduction technique or method, right? So basically what the PCA is trying to do is to go from those 20 dimensions to maybe 2 or 3 dimensions and keeping the same information. So you're trying to keep the same information you have in the 20 dimensions with only 2 or 3 dimensions. Important things about the PCA. So every PC, so every axis in this plot is a principal component. You're trying to retain or that every PC in that principal component analysis retains a fraction of the variability in the total of the 20,000 dimensions, right? And that is something that you always need to plot and I always recommend. In this case, for example, the principal component 1 retains 62% of the original variability in theory, right? Or what is the same? It retains 62% of the information that you have in the original data. When you do the analysis, all the PCs are sorted from the ones that retains the most to the one that retains the least. So if you're plotting PC1 and PC2, in theory, you are having the most information be present in two dimensions. In this case, we have 62 plus 15. What we have, like 77% of the information, the original information, you have it in this plot, which is pretty good. So you're going from 20,000 to 2 dimensions, and still you have 70% of the information being present.
So why is it lesser on the second dimension?
Well, it's been sorted.
Sorted between the 2 dimensions?
No, between all the dimensions.
Between all the dimensions?
Yeah.
So we first to get the maximum variability is covered.
Yes, so when you do the principal component analysis, you're going to obtain new axes in your data. You can have as many axes as genes, whatever dimension has the lowest, and you sort them. So from the highest dimension to the least dimension. Every PC is a combination of genes. So we're talking about bulk RNA-seq. I'm going to talk about genes in this case. So every principal component is a combination of genes, which you give different weights. So I'm not going to go through the process of how you create the PCA, but that's the main idea. You need to think about it that PC1 is a combination of genes, and on every gene has a different weight on it. And talking about weights or loadings, in the case of principal components, they call them loadings, because you can access that information later if you want to.
It is trying to capture the information of all the genes, how best it can be fit in 2 dimensions.
Yep, correct. Yes. Yep.
Something kind of a best fit kind of a thing, or best match to the original.
Yep, best match to the original data, but creating new dimensions that doesn't have to do anything with the genes itself, right? So new dimensions, and this new dimension is a combination of genes, and every gene has a different weight on that.
Suppose to begin with your sample group is too heterogeneous.
Sorry?
To begin with, if you know that your sample is the group of people or patient that you're studying is too heterogeneous,
Yep.
these of interest, and if PCA plot doesn't work, what is the next choice that you go for?
What do you mean it doesn't work? PCA always works. There's no, doesn't work.
Is not fitting into
What your expectation? Okay, that's a different thing. So that your assumption that the gene expression is a function of your expectation or condition or treatment doesn't fit, you cannot do anything. Well, you can do things, but we're going to fix it. But I'm saying the PCA is not going to lie. It's going to tell you your expectation doesn't fit. I'm going to see in the next slide we're going to talk about it.
we can increase the replicates.
Oh yeah, you can make decisions like this. Yeah, increase the replication. Totally. Yes. Yeah. Yeah. So and 2 more important things. One other thing, basically one of the goals is to check, do my samples cluster, right? So you can color them by your conditions. Let's say we have blue drag, green drag, and red drag. Do they cluster based on this? It seems so, right? So red samples go together, blue samples more or less go together, and green samples go together. You can assume, oh, I have good clustering. So it seems that my expectation that expression relates to my treatment, right? It seems to be true in here, or more or less true. You can also look at how much variation you have within group. The green and the blue ones, since there are more variation, but it's still more or less clustered together. But it's really important to retain that idea. PC1 is the one that has the most information here, right? And PC2 is the second one. You can even plot PC3, or if one day you discover how to do 4 dimensions, then you can even plot PC4.
Should we discuss sometimes we get so much variability? Should we have done all the experiments. Now
Yep.
we have this much of data.
Yep.
So whether we should remove some genes or how we can rectify that? Can we fix those the genes?
Let's talk about this next, how we can try to fix. But there's no fixing per se. There's modeling, and we can talk about that. Let's see if I'm answering the question in the next slides. Well, what I was saying, right? So pretty much this PCA is telling, yeah, my expectation that the condition under study is the main reason that is producing that changes in expression, it's true. We know that it's not everything because there's some variation here, right? I mean, not every dot is on top of every dot. There's other things happening, but it seems that the main source of changes is your condition. So here we have an example. So there are mice growing in a lab, right? And I'm a good experimentalist, and I've been keeping track of this information. I'm working with 2 different strains of mice. I've been keeping track where they're coming from in different cages, so I know where the cages are coming from. I know which one are treated and which one are not treated, and also keeping track of the sex of that animal, right? So that is a good practice. And generally, we call these the metadata of our samples. So I've been good keeping track of the metadata of my samples. I've been good. I've been keeping all the information, as much information possible I could. So, but the main goal was I'm expecting that the treatment is the main source of variability in my data. Is it the case? No, right? So in principle, if I'm plotting PC1 and PC2, I overlay the information about treatment. There's no clustering here. Say, okay, what can be other source of variability in my data causing these separations? Yeah, it could be, right? So let's look at it. So we know this is not true. At least it's not the main source of variability in our data. Could it be the cage? Doesn't look like, right? So at least PC1 and PC2 is not telling us there is a cage problem here, or cage is causing difference in the expression. Could it be the sex? Yes, yes, or maybe? Is it the main source of variability in the data? No.
All the blues are not together.
Right? There's some clustering. We see blue on top, red on the bottom. PC2 is separating the sex. So sex seems to be the second source of variability in our data, but there's still something else. It could be the strain of mice, right? There's only one left. So, oh, sorry, so I'm going a little bit farther here, but yes. So when we do strain of mice, let's imagine this is a little bit more complex than my idea to show here. But yeah, when we do strain of mice, all of a sudden PC1 is separated in red or blue with one exception, right? So, but yeah, a strain of mice is the main source of variability in the data. The genomics of that animal is telling a lot about the changes in expression. PCA also may help you with sample swapping, and that's why you have a red dot in the blue section and a blue dot on the red section, and a blue dot and a red dot on the blue section. So when you see these situations where everything clusters perfectly except 2 samples, oh, you need to review your notes and be sure you didn't do a sample swapping, because probably it's what is happening here, right? But I mean, I made up these cases to show that you can use it for that too. But yeah, the main idea was that the strain was the main source of variability in the data. But you can plot more PCs. You don't have to stop with PC1 and PC2. And if we plot PC3 and PC4, and then we do the treatment, all of a sudden PC3 is separating the 2 colors.
Whether this will have same variability, the data, the percentage of data?
Well, that's a good question, right? I didn't plot it. So you,
That's what I'm asking.
yeah, no, that's a good question. I didn't plot it, so we don't know yet. But it's true that, so one thing we can know for sure is this, right? So if we try to plot the weights of every, let's say, factor affecting the expression, the main factor is being the strain. We observe that. Second one is going to be the gender. The third one we know is the condition of the study based on the PC3. And there's other things that we don't know for sure, right? And your question is how much the condition of the study, right? We need to know the percentage of variability explained by every PC to figure out that to some extent. Before we answer that, so again, I'm going to insist on this formulation. Now we have a different way to look at our data. Originally, we said expression depends on condition. Now we can say, what if we add more factors to our formula? Now the expression depends on strain, gender, and condition. So we can formulate that and resolve the equation too. So we can separate the effect of condition, we can separate the effect of gender, and we can affect the effect of a strain. If we have time tomorrow, we can try to do an exercise like this. The first one is going to be only assuming that we have one condition and that's what affecting the expression.
So
But this is, again, keep this in mind because it's important in the way that you need to imagine linear regression, right? When we do y equal x and whatever the other factors, whenever when you do any kind of linear regression. Same idea. Oh, okay.
How many slides do you have?
I can finish in 8 minutes.
Yeah, okay, because we'll break for lunch.
Okay. Well, they don't need to have lunch. They get feed by information. So I'm going to go quick because we are in a rush. I think everybody's hungry here. I don't know why. So you have a question. Somebody asked me this before, maybe, I don't know. So imagine these situations, right, where all of a sudden everything clusters together really nicely, more or less, at least for PC1. You have ones that have a lot of variability. This is bad situations in the sense that this analysis is going to be more complex. In those cases, I would recommend analyze blue separately. If you care about this, and we can go into details. If somebody has questions about this, I'll answer them. But you can have situations like these, and then you need to make decisions on how you analyze your data, because one of them is not going to be, is going to throw off the statistical analysis just because the intervariability within the data is too high.
So we will not get significance in the data.
Yeah, you're going to get a lot of problems with that. And we can talk about the problems too if we have time. The other one is, I mentioned that every new dimension that we create, every PC is a linear combination of genes. So if you care about why PC1 is separated green from red and blue, you can look at the main genes and say, oh, these genes are the ones that are causing this separation. So you can even look at those. The other question was how much information each one of them has, right? That's important to do. So these, they call them scree plots, I think, sometimes. So you can plot every dimension and see how much do they explain. So in this case I'm showing here, it's not the same, right? But it is another example. PC1 only explains 26%. So it's not that great. So if we only plot PC1 and PC2, we barely reach 50%, right? So we're probably going to need to, to plot other dimensions to see what is happening here. So it's always good to plot, don't plot PC only, PCA, plot both of them.
So can we modify according to our
No, you could modify your formula, but you're not going to use the percentage of information for anything, just for you to know how much, because you're not going to be able to change that. It's your data. Your data tells this. That's it. So if your data is really flat, it's going to be really hard to explain, right? It's going to be almost impossible. We can skip that for now. I'm going to try to go fast. So we talk about batch effects, so technical problems, technical batches, not biological batches in that sense, but technical ones. Generally, when we talk about batch effects, it's related to technical issues. So there's a lot of ways to control them, and you've already been talking about it, right? One is controlling the animals in the lab, right? That's a good way to control it. Choosing always the same machine to sequence. Don't change the sequencing machine. The same person doing the experiment all the way is always a good thing to do, right? So if you change person, they may change a little bit how they pipette. You try to control as many variables as possible. If you cannot control them, take notes. So then you can make decisions later about how you want to model your analysis. And that's an important one, right? So you don't want to do your controls on Monday, and then a year later you do all your treatments. Because then that time period, you're not controlling it for anything. You should mix. So if day one, if you could do both of them, it's going to be better. Because you are not confounding the effect of time in your analysis.
But in the human studies,
You do as much as you can, right? And then you take notes again. You use metadata for those things.
so we should run before treatment or after treatment, even if we are getting sample after 6 months together.
Well, you have to. You have a choice, right?
In the same
Yeah. So if you don't have a choice, it's whatever you have. I'm not going to go through this. Okay. So your map and t-SNEs we mentioned before. This is a little bit of beef that I have with plotting in papers where we said before, a plot needs to tell a story. It's not enough just to tell it's nice, right? So t-SNE and your maps are also dimensional techniques. So the question was, we were talking before, is if you plot something in a paper, it needs to tell a story, or even more than that, you need to talk about that story, right? So another plot that I want to mention that sometimes we use for QC. So you've seen this before, right? If you've seen an RNA-seq paper, heat map is the other thing they want to see, right? Or it's the first thing they ask for, a heat map. Do I need to explain what a heat map is? Generally, when you presented is some sort of genes in rows, you generally see a clustering of the genes and a clustering of the samples. So going fast to this, do you think the PCA and the heat map tells the same story? Or let's put it differently. So do you think that there's a good clustering of samples here?
Yes, it seems, but not an broad. Yes, it depends.
It seems. Anybody wants to say something stronger? Yes or no?
Yes.
We don't know. I tell you why we don't know. I don't know how they selected those genes. So I've seen papers, and I think this is one of them, that they say, oh, I'm plotting a heat map with the genes differentially expressed. If you pick what generates differences, you get differences, right? In the PCA, we're not picking. We're taking pretty much everything and doing a plot. In here, I'm picking genes that created the difference, so you're going to see differences. So this is not telling us anything, absolutely anything, right? So why do plot it? Why? But it's true, we always do it. Every time we do a heat map, we plot the clustering of the samples, and sometimes we plot genes that are already creating differences.
No, but it's telling that these three samples have this much of expression, right? So whether they
Yes, but you need to do, I agree with you, but you plot the clustering. No.
I'm already picking.
Yeah. Yeah. So why you do the clustering? Default, I agree. It's the default, everybody does it, it's fine. But why to plot it when it's a story, right? So humans, I see that a lot. When you do non-model organisms, pay attention to those things. I don't know why humans or I don't know. It's a completely different story when people or experiment with non-model organisms, they pay attention to those things. So, some take-home message before we leave for, but you already know them. Replication, 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 replication. We can summarize the whole. RNA-seq, there's no process you do depending on your goal. So think about the what is your final trying to do differential gene expression analysis, transcriptomic differential expression analysis, and that's it. Another quote that I like though. I like this one especially. Here, to console a statistician, when is finished, is often merely to conduct a post-mortem examination. And that happens to us all the time. To us when they already done. What are we going to do? Nothing. We cannot do anything to change it. Lunch.